Okay, very good afternoon, one and all. So in the last class, we have started frequency shift keying and even we have completed the generation principle of FSK. So already we defined FSK signal as the change in the frequency of carrier component with respect to change in frequency of carrier signal with respect to input B of t. So that is generally called as FSK signal. So this FSK signal is defined as AC cos 2 pi FCT plus omega for input data bit 1. And if the input data bit is 0, it is 2 pi FCT minus omega. So there is a decrease in the frequency. That decrease in the frequency is defined as low frequency FL and increase in the frequency is defined as high frequency FH. And we discussed in the last class that let us replace FC plus omega by 2 pi as FH and FC minus omega by 2 pi as FL and replace AC as root 2 PS. And then you can get the expression for FSK signal as AC cos 2 pi FHT when input data bit 1 and AC cos 2 pi FLT for input B of t 0. Now you can also define the expression in terms of root 2 PS also. And later what we did, and later we have defined the above two expressions in terms of 1-bit energy carrier. So here we will have two 1-bit energy carriers because here the carrier frequency changes by two distinct frequencies. One is high frequency component when input data bit 1 and low frequency component for input 0. Okay, so that's why we need to express the above expression in terms of the corresponding two 1-bit energy carriers. Both are represented in terms of FH and FL. So please replace the above expression in terms of phi1 of t and phi2 of t. What is phi1 of t? Phi1 of t is a 1-bit energy carrier due to the frequency FH and phi2 is the 1-bit energy carrier due to the frequency FL. Okay, so where phi1 of t is root 2 by ts into cos 2 pi FHT and phi2 of t is root 2 by ts into cos 2 pi FLT. So already we have defined the generation principle for FSK signal. The input is the binary sequence, which is a digital signal, and using that signal we should convert it into FSK. How can you generate FSK signal? By using two carriers. What are the two carrier 1-bit energy carriers? One is due to FH and other is due to FL. Now our B of t, please observe the generation principle. The B of t is split, it's directly equal to BH of t and inverted form of B of t will be considered as BL of t. What is BL of t? Inverted form of B of t and BH of t is directly equal to B of t. Okay, so if you so coming to the generation, it consists of two modulators. One is the upper modulator and other is lower modulator. Upper modulator, see both the modulators are a combinations of level shifters and multiplier. So level shifter like shifts the magnitude by a factor of root PSTS. Okay, so whenever the upcoming data bit, for example, if it is 1, the BH of t will be 1. So you will get the product as SH of t. But at that time when B of t 1, our BL of t will be 0. So that's why 0 multiplied by any carrier gives you SL of t as 0. So whenever B of t is 1, the output is due to upper modulator, that is SH of t. And whenever B of t is 0, the output is due to lower modulator because when B of t is 0, BL of t will be 1. So 1 multiplied by the corresponding carrier gives you SL of t. So whenever B of t is 1, output is due to SH of t. Whenever B of t is 0, output is due to lower modulator, that is SL of t. So both SH of t and SL of t are applied to the summer to generate FSK signal. So already we have seen the generation principle. When B of t is 1, BH of t will be 1 and BL of t is 0. So output is SH of t. This is from the upper modulator. And whenever B of t is 0 and BH of t will be 0 and our BL of t is the inverted form. So that's why it is 1. So at that instant output is due to the lower modulator. So in the generation principle we define the upper modulator output as SH of t whose input is BH of t. And the level shifter data is root PSTS and phi 1 of t is root 2 by Ts into cos 2 pi FHT. Similarly, what is the output from the lower modulator? We assumed it as SL of t, which is BL of t into root PSTS into root 2 by Ts into cos 2 pi FLT. Where this root 2 by Ts cos 2 pi FLT, you can assume it as 1 bit energy carrier due to low frequency. Take it as phi 2 of t. Okay, the sum of these two outputs obtained from the product modulators is the total BFSK signal. So our BFSK signal, which is the output from the, which is the sum of outputs obtained from the two modulators, that is SH of t plus SL of t. Where SH of t, please replace BH of t into root PS into TS into phi 1 of t plus BL of t into root PS into TS multiplied by this factor is phi 2 of t. And also you can define the symbol energy E suffix S as the product of power dissipated per symbol and symbol duration. And please remember that if you are transmitting only 1 bit per symbol, in the binary FSK we are transmitting only 1 bit per symbol, but with two different frequencies. Okay, so because we are transmitting only 1 bit per symbol, here the symbol duration will be equal to bit duration. So ES will be equal to EB, or else in other sense you can also call that TS is equal to TB. If TS is equal to TB, PS into TB will be the bit duration, that is E suffix B. Okay, now finally you generated BFSK signal, which is the combination of BH of t and BL of t. Please remember this equation. Okay. Now already we evaluated the Euclidean distance. So we defined that the Euclidean distance is high, then only our probability of error will be low. So Euclidean distance for two orthogonal carriers will be very high. So that's why we assumed the case considering the carriers as orthogonal to each other. So that's why both are perpendicular to each other and each has a magnitude of root PSTS, that is nothing but root ES. Okay, so root ES on x-axis and root ES on y-axis. So using Pythagoras theorem, you can obtain it as C as root of a square plus b square, where a is the magnitude of x-axis and b is the magnitude of y-axis. So root of root e square plus root e square. So root and square gets cancelled in first and second terms. So you will get root of 2es. So you can also define it as root 2 into ps into ts. Okay, if you want to compare the Euclidean distance of FSK with ASK and PSK, the Euclidean distance of FSK, it is less compared to PSK because our PSK Euclidean distance is very high. So that's why PSK probability of error is very less. Okay, but our Euclidean distance of FSK is greater than ASK. So that's why you can say that the probability of error for FSK is less compared to ASK. So as a comparison here you can say that in terms of probability of error, it's less for PSK and it is very high for ASK. And our FSK will shuffle between ASK and PSK. The best performance will be provided by PSK in terms of probability of error, in terms of less probability of error. And even like high noise immunity. Okay, this part we studied in the last class. And even we discussed this one. So left column represents the time domain descriptions of the input signal, carrier signal and modulated signal. Okay, so our input signal is a digital signal. Okay, here we assumed 1 0 1 0. Okay, and the carrier as usual, let us assume it as AC cos omega ct. Let the amplitude be AC and frequency be FC. So what is FSK signal? FSK signal has higher frequency, for data bit 1 and lower frequency for data bit 0. The high frequency for data bit 1, the high frequency for data bit 1 is represented by compressing the signal in time. The low frequency for data bit 0, the low frequency for data bit 0 is represented by expanding the signal over time. So by compressing and expanding the signal over time, you can represent the high frequency and low frequency components respectively. Okay, so finally you represented the our signal B of t, carrier C of t, and FSK signal SFSK of t. Okay, so these are the signals present in the time domain. So they represented in the first column, and second column figures represent the spectrum, the corresponding spectrum of the figures shown on the left side. So first figure in the second column represents the spectrum of B of t. So our input signal is always a band limited between minus FB to plus FB. So that's why the spectrum of B of t will lie from minus FB to plus FB. So being the input signal band limited to minus FB to plus FB, we have represented the spectrum range from minus FB to plus FB. That's all. Okay, where FB is a reciprocal of bit duration, where FB is the bit frequency which is reciprocal of bit duration. Now second figure in the second column represents the carrier frequency. So already you know that carrier frequency is high compared to bit frequency. Okay, carrier frequency is high compared to input signal. So that's why FB is made close to 0 and our FC is somewhat made far away from 0. Okay, FC is greater than FB. So like that accordingly represent the value of FC. Next, third figure is our FSK modulated signal. Please observe the FSK modulated signal. Please observe the spectrum of FSK modulated signal carefully. If you observe the spectrum, please once let us recollect the generation principle. To generate FSK signal, you need to generate two kinds of signal frequencies. One is FH and other is FL. So in the transmitter section, this FL component is multiplied by some BH of t. Once again, BH of t is it's a band limited signal that range from minus FB to plus FB. If this BH of t is multiplied by cos 2 pi FHT, our spectrum of FH will move from plus or minus FB. That is, FH will move from FH minus FB to FH plus FB. Once FH is multiplied by plus or minus FB, you know that you will get only two sidebands. This is the principle of double sideband suppressed carrier. Here carrier gets suppressed, but two sidebands will exist. That is FH minus FB to FH plus FB. This is due to the upper multiplier, and the lower multiplier takes the product of BL of t and the phi 2 of t carrier, where phi 2 of t is root 2 by ts into cos 2 pi FLT. So once FL is multiplied with the input BL of t, our FL will also you will obtain LSB and USB, where LSB for FL is FL minus FB and USB for FL is FL plus FB. So finally you got the whole spectrum of FSK signal consisting of lower frequency FL, which is less than FC, and higher frequency FH, which is greater than FC. And FH will have two sidebands, FH minus FB to FH plus FB. Similarly, FL will also have two sidebands because this is the multiplier output, FL minus FB to FL plus FB. Now please observe this carefully, and for evaluation of bandwidth, you need two sidebands. One is what is the lower cutoff frequency and what is the upper cutoff frequency. Please observe the spectrum carefully and tell me what is the lower cutoff frequency and what is the higher cutoff frequency of FSK signal. Then only you can calculate the bandwidth, because bandwidth is defined as the difference between upper cutoff frequency and lower cutoff frequency of the corresponding spectrum. Please observe the spectrum carefully and tell me what is the lower cutoff and what is the upper cutoff of the whole spectrum. Any one of the student, please respond. Respond, please. What is the lower cutoff frequency and what is the higher cutoff frequency of the spectrum shown here? So total of 39 students are there. Okay. So any one of you please respond, what is the lower cutoff and what is the higher cutoff? Now it's almost all 3:20. I will take the attendance. Okay. So any one of the student please respond. See, total of 39 students are there. No one is not yet responding. See how many students are there. Please, any one of you respond and tell me what is the lower cutoff and what is the higher cutoff. See, are you there or not? Any one of you respond. What is the lower cutoff and what is the upper cutoff? I1, I1. I1, I5, I5, J0, J0, J1, J1, J5.
Yes, ma'am.
Cheppandamma, what is the lower cutoff and what is the upper cutoff for the spectrum shown here?
FH plus FB.
FH plus FB is the higher
Upper
cutoff.
cutoff.
Okay, very good. What is the lower cutoff?
FL minus FB.
FL minus FB. Okay, very good. Then what will be the bandwidth? Difference between upper cutoff
Upper
and
cutoff,
lower cutoff. Okay, so upper cutoff frequency is FH plus FB. Please observe here. Okay, thank you. J5. So upper cutoff is FH plus FB and the lower cutoff is FL minus FB. So if you take the difference between those two, it will be FH minus FL plus 2FB you will get, plus 2FB. So under the assumption that FH minus FL as 2FB under the assumption that FH minus FL as 2FB. Okay, please assume like that, and 2FB, 2FB, you will get 4FB. So what is the minimum bandwidth required for FSK signal? What is the minimum bandwidth? 4FB. And what is the bandwidth of either ASK or PSK? Any one of you, please respond. What is the minimum bandwidth needed to transmit FSK, ASK or PSK signal? How much? 2FB. So minimum bandwidth needed to transmit FSK signal is 4FB. And if you want to compare it with either ASK or PSK, so the minimum bandwidth required for either PSK or ASK is 2FB. So the minimum bandwidth of FSK is always twice to that of either ASK or PSK. So that's why in terms of bandwidth, our FSK signal will have a least performance. So that's why FSK is a least, like you can say, FSK system is least bandwidth efficient system, because it's you need a lot of bandwidth. So 4FB amount of bandwidth is required to transmit only one bit. So in order to transmit a single bit, you need 4FB bandwidth. Okay, so that's why in terms of bandwidth, you can say this is a least performer. Okay, so first statement is regarding the multiplication of our carrier component FH with BH of T in the upper modulator, and second statement is the product of, in the second statement I told you the product of BL of T with BL of T signal with FL to generate the SL of T from the lower multiplier, so that the frequency range will be from FL minus FB to FL plus FB. Okay, and upper multiplier spectrum range is from FH minus FB to FH plus FB. So if you, because the FSK signal is a combination of SH of T and SL of T, the total spectrum range from FL minus FB to FH plus FB. So difference between the upper cutoff and lower cutoff gives you the bandwidth of whole BFSK signal. So that's why we took FH plus FB minus FL minus FB. So what is the assumption here? Assumption is FL is less than FH, and second assumption is FH minus FL is equal to 2FB. So upon assuming like that, so this is our minimum criteria. So assuming the minimum necessity, what is the minimum bandwidth required for BFSK signal transmission? 4FB. So the minimum bandwidth required to transmit FSK signal is 4FB. Okay, so if you compare that with either ASK or PSK, it is twice the amount of bandwidth required for either ASK or PSK. So that's why like FSK is least bandwidth efficient system. Now let us move to the FSK demodulation techniques. So you can see two types of demodulation techniques are available similar to ASK. So here two techniques include the coherent and non-coherent detection. See, so in ASK also we defined what is coherent detection. So coherent detection, also called as synchronous demodulation technique, the technique uses synchronous carriers. So that's why the probability of error for coherent detection is less. Probability of error for coherent detection is less. But the generation of coherent carriers is somewhat difficult, because to generate coherent carrier you should undergo both frequency and phase synchronization as well as timing synchronization. So generation of coherent carrier is difficult, but it gives you the signal with less probability of error. Okay, and second one is non-coherent detection, which is also called as asynchronous demodulation. In the non-coherent detection, we don't make use of synchronous carrier. Okay, so that's why generation principle is easy, but in terms of probability of error, we have high probability of error for non-coherent detection and less probability of error for coherent detection. But generation of coherent carrier is difficult. Okay, based on the necessity, you can opt either coherent or non-coherent detection. Generally, non-coherent detection techniques are used for laboratory applications. Okay, and coherent detection you can use for real-time applications. So please go through the coherent detection. So similar to the transmitter section, here also the circuit needs two detectors. So similar to the transmitter section which used two modulators, the receiver section also uses two detectors. Okay, two synchronous detectors are used. So those detectors are two correlators. One is correlator 1 and second one is correlator 2. The input to the receiver is the FSK signal, that is the modulated signal, that is simultaneously fed to both upper correlator as well as lower correlator. Okay, upper correlator, what it will do? It will take the, each correlator is a combination of multiplier and low pass filter. Each correlator is a combination of multiplier and low pass filter. Upper correlator, what it will do? It will multiply the incoming BFSK with cos 2 pi FHT. Okay, and that component is fed to the low pass filter. Let us assume the low pass filter output be L1. This is from the upper correlator or correlator 1. And next incoming BFSK signal is fed to the correlator 2. Okay, correlator 2 also consists of multiplier followed by low pass filter. This multiplier will take the product of BFSK signal with cos 2 pi FLT. Okay, the product is fed to the correlator, low pass filter. This low pass filter output, let us assume it as L2. Okay, now L1 and L2 both are compared. L1 and L2 both are compared to generate the output as 1 and 0. Okay, comparator output is 1 if L1 is greater than L2. Comparator output is 0 if L1 is less than L2. Okay, now let us please wait for 1 second. See, here two coherent carriers are used at the receiver section. Two coherent carriers are used at receiver section. Please wait for 1 second. Okay, here two coherent carriers are used at the receiver section. The input to the receiver is BFSK signal, which is in the form of, please observe, the input to the receiver is BFSK signal, which is in the form of, what is the general expression for BFSK signal? Root 2PS into BH of t into cos 2 pi FHT plus root 2PS into BL of t into cos 2 pi FLT. Okay, this is the FSK signal general form because it is a sum of output due to the upper product modulator and output due to the lower product modulator. That is SH of t plus SL of t. Okay, so now this signal is received by the receiver section. It's collected by the receiver section. Now receiver, already I told you, receiver consists of two correlators. So the output of upper correlator is L1 and output of lower correlator is L2. Let us take the upper correlator first. Let us calculate the output of upper correlator. So correlator consists of multiplier followed by low pass filter. Okay, so the output of upper multiplier is, multiplier what it will do? Upper multiplier takes the product of FSK signal with cos 2 pi FHT. And lower multiplier takes the product of FSK signal with cos 2 pi FLT. Let us calculate the output of upper multiplier first. So it is root 2PS into BH of t into cos 2 pi FHT plus SL of t, that is root 2ps into BL of t into cos 2 pi FLT. So this whole thing is FSK signal. Now this is multiplied by cos 2 pi FHT. Cos 2 pi FHT. So if you multiply this cos 2 pi FHT, you will get cos square 2 pi FHT in the first term. And in the second term, you will get the product of cos 2 pi FHT into cos 2 pi FLT. Okay, so first term is cos 2 pi FHT, cos square. So cos square x using trigonometric expression, you can say it as 1 plus cos 2x divided by 2. Okay, and here in the second term, you can take the product of some cos x into cos y. So cos x plus 5 plus cos x minus 5 divided by 2. So using the respective trigonometric expressions, we replaced. Now this is the output of upper multiplier. So already correlator consists of multiplier followed by low pass filter. Now this whole multiplier output should be fed to the low pass filter 1. Now I am telling you that the low pass filter do not allow the higher frequency components and the mixed frequency components. Now what is the output of the low pass filter? Please any one of you tell me, if the multiplier output is fed to the low pass filter, what is the low pass filter output? So low pass filter do not allow higher frequency and it won't allow mixed frequencies. What is the output of a low pass filter then? Any one of you?
Lower frequency component.
What is the lower frequency component here? FH it won't allow. FH plus FL as well as FH minus FL it won't allow because these two are mixed frequencies. Then what is the output of low pass filter? Only the DC component. What is the DC component?
Root 2 PS.
Root 2 PS. ఇక్కడ 1/2 ఉంది కదమ్మా. This
Yes,
1/2 is a DC term. That 1/2 multiplied by root 2 PS into BH of t. Okay, is it okay?
Okay, ma'am.
And these higher frequency and mixed frequency components are not allowed by the low pass filter. Please, we can see it in the next slide. So low pass filter 1 do not allow mixed and higher frequency components. Therefore, the output of low pass filter will be half, that is the DC component, into root 2 PS into BH of t. So take this 2 inside the root so that you can get root PS by 2 into BH of t. So similarly, what is the output from the lower correlator? So in the lower correlator, FSK signal is multiplied by cos 2 pi FLT. So once you multiply like that, the low pass filter will not allow all the higher or mixed frequency components. So the output of low pass filter L2 will be root over PS by 2 into BL of t. Okay, so the output of upper low pass filter is L1. Let us assume it as L1, which is root PS by 2 into BH of t. Similarly, the output of low pass filter is L2. Let us assume. Okay, so it is equal to root PS by 2 into BL of t because you are multiplying with cos 2 pi FLT. Okay, so now please observe L1 is proportional to BH of t with a proportionality constant of root PS by 2 and L2 is proportional to BL of t with a constant of root PS by 2. So we can say that the low pass filter outputs are proportional to either BH of t or BL of t based on the corresponding frequency used. If you use cos 2 pi FHT as the multiplier input, you will get BH of t. If you use cos 2 pi FLT in the lower correlator, you use like that, then you will get the signal proportional to BL of t. Okay, so low pass filter outputs L1, L2. Now both the outputs are fed to the comparator. Okay, what the comparator will do? Comparator takes the two data obtained from low pass filter 1 and low pass filter 2. Okay, both are fed to the comparator. If L1 is greater than L2, comparator output is 1. If L1 is less than or equal to L2, comparator output is 0. Okay, so finally you can obtain the comparator output as 1 if low pass filter output is greater than low pass filter 2 output. So if upper correlator output is greater than lower correlator output, data is assumed to be 1 and data is decided as 0 when lower correlator output is greater than upper correlator output. This is about the coherent detection. And what is the advantage of coherent detection? Probability of error is less because you are using synchronous carriers. Which carrier is used in the upper correlator? Cos 2 pi FHT. Which correlator is used in the lower correlator? Cos 2 pi FLT. So that's why, because you are using proper synchronous carriers, the probability of error in coherent detection is very less. This is about the coherent detection. Now let us move to the non-coherent detection. So similar to binary ASK technique, here also we'll use envelope detectors. Okay, envelope detectors extracts the magnitude of lower frequency component. Please observe the circuit carefully. This non-coherent detection technique is also called as asynchronous detection, asynchronous demodulation, because it don't make use of any kind of synchronous carrier. Here please observe, anywhere you are using any cos 2 pi FHT product like that. So you are not at all using any carrier components, synchronous carrier components. But in the case of coherent detection, we used cos 2 pi FHT as a synchronous carrier in the upper correlator, and you used cos 2 pi FLT as the product in the lower correlator. Okay. Now, because you are not using synchronous carrier, it will increase the probability of error. Because you are not using synchronous carrier. So even though the circuit is simple, but the probability of error is more in this kind of non-coherent detection. For laboratory applications, you can use this kind of non-coherent detection technique. This is enough. See, please observe the circuit. The incoming BFSK signal is applied to, here also two non-coherent detectors are used. Okay, so first upper non-coherent detector and lower non-coherent detector, and both the non-coherent detectors once again consists of band pass filter, envelope detector and sampler. See, envelope detector once again in turn it consists of rectifier followed by low pass filter. Okay, similarly, please observe the band pass filter cutoff frequency of upper non-coherent detector. It is FH. And the band pass filter cutoff frequency for the lower non-coherent detector is FL. Okay, so the incoming FSK signal is applied to the band pass filter, upper band pass filter. It will allow only the FH component, and our lower band pass filter, it will allow only the FL component. But our FSK signal is a combination of both SH of T and SL of T. But our upper detector allows only higher frequency component, and the lower band pass filter allows only the low frequency component. Okay, so the upper band pass filter is applied to the envelope detector. What this envelope detector will do? So it consists of rectifier and low pass filter. So rectifier, like it consists of a diode. Okay, it consists of a diode. So under the forward bias condition, it will act as a short. Whenever there is no signal, it will be off. So whenever during the upcoming signal, the signal will be converted into pulsating DC. Okay, so the alternating component will be converted into pulsating DC, and that pulsating DC is smoothed by the low pass filter, because low pass filter acts as a approximation filter. Because low pass filter acts as approximation filter, it smoothens the pulsating DC obtained from the rectifier. So the low pass filter output is applied to the sampler. But in the ASK, directly the low pass filter outputs are compared. Directly the low pass filter output is compared with the threshold by using decision device. Here we are using a sampler. Okay, please compare the non-coherent detection of BFSK with BASK. Almost all the principle is same, but here we used two non-coherent detectors, one in the upper side and other in the lower side. Okay, and here the sampler importance is sampler will convert the DC component, or you can say that the DC component is collected at some distinct intervals. Sampler discretizes the time. Okay, sampler takes the smoothened DC obtained from the low pass filter, and it is defined at some discrete intervals. Let the sampler 1 output be L1, and similarly let the sampler 2 output be L2. This is due to the low frequency component, because the band pass filter used in the lower detector will allow only the FL component. So if L1 is greater than L2, comparator output is 1. If L1 is less than or equal to L2, here L1 is less than or equal to L2, then the comparator output is 0. Please let us move to the next slide. You can see the general expression for BFSK. Already you know the FSK signal general form. It is root 2ps into BH of t into cos 2 pi FHT plus root 2ps into BL of t into cos 2 pi FLT. Once the whole signal is applied to the non-coherent detection, we have two bandpass filters. The first bandpass filter will allow the first term. What is the first component? It is due to high frequency. That is root 2ps into BH of t into cos 2 pi FHT. And the second component is due to FL. Because second bandpass filter will allow only FL component. That is root 2ps into BL into cos 2 pi FLT. Okay, first component is due to FH, because first bandpass filter will allow only FH component, and second bandpass filter, which is used in the lower detector, will allow only FL component. Okay, so first term is the output of bandpass filter 1. Second term is the output of bandpass filter 2. So what I mentioned in the second statement. Bandpass filter used in the upper detector allows FH component. Okay. Similarly, bandpass filter used in the lower detector allows FL component. Please see, the rectifier converts the incoming signal the rectifier converts the incoming signal into pulsating DC, and that is smoothed by the low pass filter. Here the sampler generates the smoothed DC component at distinct intervals. Okay. See, both are compared at the comparator, and when L1 is greater than L2, total output is 1. And when L1 is less than or equal to L2, comparator output is 0. Now let us move to the advantages and disadvantages of FSK signal. Please go through the advantages. What is the first advantage? Here FSK signal has no amplitude variations, because in FSK and PSK, the modulated signal has no change in the amplitude. The amplitude is constant. So that's why it is less susceptible to noise over ASK. That is the first advantage. And what is the second advantage? the Euclidean distance of FSK. What is the Euclidean distance of FSK? It is root 2 into PS into TS, or you can say root 2 ES. It is root 2 ES actually. It is root 2 ES. It is 2 ES. Okay. And it is more than that of ASK. So that's why its probability of error is less compared to ASK. Okay, probability of error of FSK is less compared to ASK. That is the advantage, but it is more compared to BPSK. That is our drawback, because I told you the Euclidean distance of FSK lies in between ASK and PSK. So Euclidean distance is more than ASK. So that's why its probability of error is less compared to ASK. And because its Euclidean distance is like less than PSK, probability of error will be less than PSK. Okay. So next generation of BFSK signal is easy, because using two frequency carriers FH and FL, you can easily generate the FSK signal, because directly you are using the multipliers like in the upper modulator and lower modulator, you are using two multipliers. Okay, so generation of BFSK signal is easy. Next, let us move to the drawbacks other than the probability of error, because the probability of error for BFSK is greater than BPSK. So that's why if you want to compare our BFSK with BPSK, the probability of error for BFSK is more. So that's why you can prefer BPSK when compared to BFSK, and you can prefer BFSK compared to BASK. So regarding bandwidth, so bandwidth of BFSK signal, minimum bandwidth is 4 FB. So that's why it is twice the amount needed for BPSK. So that's why, because it's bandwidth inefficient system, because you need lot of bandwidth, 4 times bandwidth you need to transmit FB signal, you need 4 FB bandwidth. So it's very high amount. So in terms of bandwidth, its BFSK signal has a drawback. That's it need large amount of bandwidth for signal transmission. Almost all twice the amount needed for BPSK or BASK. Okay, these are about the advantages and disadvantages of BFSK signal. And applications. FSK signal can be transmitted via telephone wires, optical fiber, or wireless media. So in general compared to ASK or PSK, similar to the PSK and ASK, we can transmit this signal via wires or even through fibers or even wireless transmission. You can use this kind of FSK signal, and this is commonly used for caller ID applications. Okay, to know the information about the caller, so you can use this kind of BFSK signal. And also it is used in paging services. Okay, where for example, if you want to send some information to a group of people or to a community, and then you can use this kind of pagers. Okay, there you can prefer FSK transmission technique, where you will have like unidirectional. So you cannot receive their data, but you can say what you want to tell by using pagers. And even you can prefer for cordless telephony. Okay, so also it is used in high frequency radio transmission applications. Okay, but the main drawback here is it needs large amount of bandwidth, and the probability of error is more compared to PSK. Okay, these are all the applications of BFSK. So any doubts regarding FSK? Any doubts regarding FSK? With this, almost all we completed the module of FSK. In the next class, we can continue with quadrature phase shift keying technique. Now, any one of the student, please tell me, out of the three techniques you studied, ASK, PSK, and FSK, which one you can prefer the most for varieties of applications? Any one of you? Any doubts regarding FSK? Say yes or no. Any doubts? Okay, already I took attendance at 3:20 p.m. Okay, you can leave the class.